And are you ready?
I'm ready whenever you are, yeah.
Hello, good morning, good afternoon, and good evening. Welcome you again to this World River and Delta System Source to Sink webinar series. Today is our great honor to invite Professor Janok Bhattacharya from McMaster University, Canada. Come here talk about source to sink in deep time, reconstructing Permo-Triassic to Cretaceous Rivers and their catchment in North America. So before I introduce Jana, and also would like to mention since August 2020, can you believe already 2 years ago, we started this webinar series. So far, we have already had 128 talks. All previous talks, including this coming one, will be, and all are already archived on our Source to Sink YouTube channel. So welcome to use this as a great resources for teaching and research. And at the same time, we also have a Source to Sink Twitter account. So you're welcome, follow us. We will make announcement for weekly talk and publication, conference, etc. So next Wednesday, same time, we have Juan Panigua Arroyo come from Colombia, come here talk about Galilei that leads to delta shift prediction. So as I mentioned, Professor Bhattacharya is from Canada, McMaster University. As you can see, he got his bachelor degree geology in Memorial University of Newfoundland, and then PhD also McMaster University. He used to be the president of the Society of Sedimentary Geology, and now serve as a Professor Susan Cunningham Research Chair in the geology. His research mainly focused on fluvial and deltic sedimentology, shales and seabed second stratigraphy and source to sink studies. I think Jonah, now I give the floor to you. You can share your screen for the presentation mode.
Perfect. We'll just do that. And does that all look good?
Yes.
Okay. Yep. Apologize if I cough a bit. I am suffering a bit of allergies. It's not COVID. I've already had that. Thank you very much. And I got involved in source to sink studies in a couple of ways. The first was through working with Jai Savitsky way back when I was working for Atlantic Richfield Company, Arco, Alaska. We were trying to figure out the geology of the supergiant oil field, the Prudo Bay Field. And Jai had a session on Arctic paleo drainage. And so myself and my colleague Bowtie went to Colorado and I got to meet Jai and really got interested in sort of being more quantitative about trying to understand big rivers in deep time. And it's an area of research that I've been pursuing now for probably over 20 years, I guess. Anyway, as Paul told you, I studied at McMaster University back in the mid-'80s, and Roger Walker was my PhD supervisor, and he, of course, is a master of facies analysis. Roger is alive and well and retired in Calgary. Jerry Middleton was sort of the master of applying physics to sediment transport. Interestingly, Jerry started his career as a hexacoral specialist and was hired at McMaster as a paleontologist and did something that no academic would consider doing today, abandoned his field of expertise and decided to get into a much more mathematical approach to physical sedimentology. Of course, Mac was a small university in those days. Jerry passed away last year, and Andrew Mile, whose retirement party I was at last night at the University of Toronto, organized a session in his honor at the Calgary Society of Petroleum Geologists meeting this summer. And I put together this talk that sort of captured a little bit of my history of research in source-to-sink systems, but also explaining how you have to combine careful field work and observations of the rocks with an increasing attention to trying to get some physics in there. And I see that Mike Steckler is on board today, and goodness, he's been sort of one of the leaders in trying to do quantitative modeling of sedimentary systems. And, you know, I remember seeing Mike's talks and like, man, this is complicated stuff, but slowly but surely I've been dragged into the quantitative world. So I'll start off with some introductions, part of it just why we're doing this kind of work in the first place, quickly review some of the source-to-sink concepts that most of you will be familiar with. Then we'll get into the actual examples that we worked on. So of course, you know, I started my career in the oil business back when I was 21 and fresh out of my undergraduate career. And the question always, if you're drilling wells, you know, the question is what's in between. And although I've historically worked primarily on deltas, which represent relatively tabular and more extensive sand bodies, as soon as you start trying to get oil and gas out of fluvial units, it gets more complicated. How wide are the channel belts? How amalgamated are they? How connected are they? How much oil is left behind or gas? And how many wells do you need to effectively improve the production? So these are the kind of questions that we had when I started working in the oil business, working for corporations such as Esso Resources Calgary, which is the Canadian branch of Exxon, and then Atlantic Richfield Company when I worked in the US. And then once I became an academic, a lot of my research was supported by consortia of up to 10 oil companies globally, including Shell, Japan National Oil Company, many, many others, all of whom are trying to grapple with this idea of predicting the subsurface. And when I became an academic, I got out of the subsurface and migrated towards outcrops, where you can actually start to see the continuity of sediment bodies. When I was a graduate student, Tony Reynolds, who just retired from BP, was a postdoc, and I was talking about the idea of the word peralic, which means of or related to the shoreline. And Tony wrote this nice paper in 1999 where he said, you know, let's try to grapple with the dimensions of sand bodies in so these shallow marine sort of channeled to delta to shoreline systems. And he put together two diagrams. The one on the right is a classic, just a plot of width on the vertical axis and thickness on the horizontal axis. And the different colors represent sediment bodies or geobodies in different environments. And although there's a lot of scatter, you can see that there's a separation of larger things. So for example, the shoreline and shelf sandstones are thick and wide. And on the red side of things, you know, crevasse channels that are little tiny offshoots at the margins of rivers are relatively small. And then on the left, he sort of shows just a visual image of the various kinds of sediment bodies that produce oil and gas. And it gives you a visual estimate of sort of the areas that they might cover with respect to the green shapes, which are some of the large assets that BP owned at the time he did the project. The Stratfjord Field and Brent in North Sea, Cusiana in Colombia. No, I don't remember where Jones Creek is, but there we go. So, you know, another approach to trying to estimate the dimensions of sediment bodies is the idea of the source to sink. And here I've modified Mike Bloom's power tools metaphors for source to sink. And he pointed out that, you know, if you drop sea level, you have two opportunities. One is you simply excavate the local material or vacuum it out and dump it in a more distal position, whether it's a delta or a submarine fan. And then he says, but there are some systems that are much bigger, what he calls a conveyor belt, where they're transferring material from a much larger drainage area. And even though sea level drops, yes, you locally excavate the material that's produced by the generation of nick points and valleys during the drop of sea level, but the bulk of sediment is really passing through the system. And so you end up with much bigger downstream sinks. And so it gets to this question of when you're looking at ancient systems, you know, what is the likely scale of the downstream sediment bodies? If you have a lot of data on the shelf and you've got some incised valleys, how big are the submarine fans that could be downstream? And what is the potential for the hydrocarbon reserves that might be in those sinks? So the idea that there are these scaling relationships has predictive value. Now, these are a series of diagrams put together by the Statoil now Equinor group. And again, they put a lot of plots together of various parameters. Here we've got the length of a river channel, the gradient, the discharge, and then on the vertical axis, they've got slope length. And they plotted dozens and dozens of these diagrams, just compiling information that says, given a shelf width, what's the likelihood of, what's the slope likely to be, or what's the discharge of a river likely to be given the width of the continental margin. And they subdivided systems into small active or young passive systems, all the way up to large passive and mixed systems such as the Atlantic conjugate margins. So another thing that we do in science is we revisit models. We try to figure out whether they're still valid. So when I was a graduate student and even undergraduate back in the late 70s and early 80s, these were the standard models for fluvial sedimentology. On the upper left is Doug Kant's diagram that suggests that there are meandering, braided, straight, and anastomosed rivers. On the bottom is a diagram from Peter Friend, who was at Cambridge at the time, who sort of suggested that mud-dominated alluvial systems are produced by quietly meandering systems, and that if you get boxes of gravel or sand, those are produced by braided streams, and never the twain shall meet. And so for many years, when I was a graduate student, we would go in the field, and the only thing you would ever worry about is whether it's a meandering or a braided stream. And this is, great classic diagrams from Bill Galloway's textbook. Bill sort of said, well, let's get away from the word meandering and braided, but let's classify streams according to the material that they carry. Are they bedload, mixed load, or severe problems with this classification, because the bedload stream still has 85% suspended mud, and the suspended load streams only have 10% more suspended mud. So, most streams, when they're in flood state, are carrying mud. There's really no such thing as a gravelly or sandy stream that isn't carrying a lot more mud. And the source to sink people, the oceanographers know this. If you talk to Jai Savitsky, say, yeah, we don't worry about bedload. It's a trivial component of the sediment budget. It's all about the suspended load. And despite the fact that they're trying to get away from using the word meandering and braided, the idea that relatively straight streams produce buckets of sand and meandering streams produce buckets of mud is still pretty entrenched within the literature. And then, and I know Jim Best has given talks in this unit. So then we get sort of the new guard of fluvial sedimentologists, and Charlie Bristow and Jim Best put together this, one of my favorite diagrams of all time. And it shows that every imaginable scenario of net to gross, in other words, the degree of amalgamation or separation of channel belts, can be explained by understanding the avulsion frequency of the river, the migration rate, so that how fast it moves versus switches, and then the aggradation rate, or if you will, the subsidence of the basin. And on this diagram, the word meandering and braided never appear. So the question is, are they even important? What is the most important thing to look at when you're trying to interpret ancient fluvial systems? And of course, as some of you may know, what is the main topic of many, many fluvial sedimentologists? It's trying to understand avulsion. It's trying to understand how rivers migrate in order to better understand this diagram. And whether or not it matters what the plan view of the river is sort of, it has been superseded by folks trying to understand the behavior of rivers. Now, the source to sink approach, there's another way of classifying rivers, and that's on the basis of whether they're collecting water, so what we call tributaries or contributaries, whether they're trunk streams, and whether they're distributaries, spreading their sediment to a wider area. And Mike, I think you've done a lot of work on the Bengal fan here, so this is your playground. And the question is, if you're looking at ancient sedimentary systems, can you make any inferences about where we are on the source to sink? Where are we? Upstream, midstream, downstream? It makes a huge difference. If you have an ancient system and you're in an upstream incised valley, it predicts that the low stands could be way, way further seaward. In contrast, if you're in distributory channels, you're close to the end of the system. And so you wouldn't be predicting a lot of sand downstream. And there is Chris Paola standing next to a nice little Cenozoic channel just up the road from Price, Utah. Here's a beautiful incised valley with a floodplain and meandering river inside the larger valley fill. And here's some nice distributary channels in the Black Hawk Formation in the Book Cliffs in Utah, just close to Price. And there's a student for scale walking along the outcrop. So let me go now to the first major example, which is the 24 billion barrel Prudo Bay Field in Alaska. That was the first big asset that I worked on when I moved from Canada to the States. And, they had this massive asset and they hadn't done a lot of geology in it. The field had been producing since about 77. We're getting almost 20 years into the production, and the concerns were about rate declines. And 1 year of production, the value of 1 year of oil production from Prudo Bay Field represented the amount of money that Seward paid to buy Alaska from Russia back a long time ago. I think it was about $7 million anyway. So Prudo Bay Field is on the north slope facing the Arctic Ocean. And here's a paleogeographic map that Bowtie and myself made, showing the present day configuration of the field. So it consists of a series of conglomeratic to sandy channels that feed a series of shore faces and deltas. And right now, the system progrades from the northwest towards the southeast. The tectonics of Alaska is very complicated. So the Arctic Alaska block is now rotated almost, what are we, about 140 degrees from its original position. So originally, the rivers fed from the southeast towards the northwest. And of course, now they've been reoriented. So it's a classic example where the original area that drained Prudo Bay has been separated from the actual deposits themselves. The basin is separated from its source. So the question is, where was all the sediment sourced from? And what was the size and scale of the rivers that fed the field? And the reason we're interested in that will become clear, I think, as I get into the geology of the field just a little bit. So Prudo Bay Field is a complicated structural and stratigraphic trap. It's got a whopping unconformity that cuts across the top of it and superimposes very impermeable shales that put a first-class seal over a very thick unit of sandstones and conglomerates that host the oil and gas. Here's an example of a geological cross-section of the field. The original gas-oil contact is the bright red stuff. Since production, a lot of the oil has been removed, and so the gas has invaded into the old oil zone, displacing the oil. In addition, they're injecting water into the field, and that further displaces the oil. When I got on board, a lot of the oil was in the lower parts of the field, which is more deltaic because the field represents a pro-delta shale to delta sandstone to coarse conglomeratic fluvial transition, as I'll show with a bunch of facies photographs in a minute. And of course, the companies that operate the field, which was primarily BP and ARCO, were concerned about where all that water was going. There's no way to sell the gas in Alaska, so every speck of gas that was produced out of the field was stripped of its liquid hydrocarbons or condensates and then pumped back into the gas cap to maintain the pressure. So I'm going to start with a little bit of what I call Roger Walker type of analysis, which is looking at the rocks. So on the left, we've got a description of a core that goes through essentially the entire productive unit and below, with a gamma log on the left, resensitivity on the right, and I'm just going to show a series of photographs that give you a feel for the nature of the sediment and the facies successions. So we start off with these beautiful sharp-based wave ripple cross-laminated graded beds. So these are little tempestites or storm beds. We've got some little horizontal burrows, maybe some little diplocraterians in here. So we have a lightly bartubated, storm-dominated succession of shell facies, which we have these little storm beds or tempestites with variably baryotibated facies. So this would be a classic storm-dominated prodelta in the Kavik Shale, which lies below the Ivishak sandstones, which is the main productive unit. As we coarsen up, we see these little upward coarsening facies successions, or parasequences, if you like the sequence terminology. There we've got a little Rosellia burrow in the middle. Again, we've got nice wave ripple to hummocky cross-laminated sandstones, and the biotubation is getting a little bit more extreme, and the facies are getting a little bit sandier. These are relatively very fine-grained sandstone, siltstones, and some claystones, relatively low quality reservoirs. As we coarsen up, we start to see laminated sands, again, with evidence of hummocky cross-stratification, and then razor-sharp contacts separating a deeper water shelf or prodelta mudstone above from the shallower shelf sandstones below. And this would represent one of these flooding surfaces. And these are used as a stratigraphic datum upon which to hang the geology to do the correlations of the overlying units. I've written papers about finding stratigraphic datums upon which to use to correlate things, and it's a complicated problem. The Prudo Bay Field was particularly difficult because above these deltas, it's all coarse-grained fluvial, and then there's a whopping unconformity, and so there were no flatline surfaces above the on top of the reservoir interval. And so the best datums were in the marine shales below, where there was a greater likelihood of finding one of these parasequence flooding surfaces that might be fairly extensive over the area of the oil field. We continue to coarsen up. You'll notice that you start to, so these baryotibated faces indicate a lot more marine and wave influence. All of a sudden, we start to see laminated, parallel laminated sandstones. There's ripple cross lamination in here. You can see in this upper very fine sand beds, and these beautiful ball and pillow structures, otherwise known as pseudonodules or soft sediment deformation, indicating deposition of sand over mud that has not lost its water. So very high preservation of water during the deposition of the sediments, implying high sedimentation rates compatible with deposition in a river-dominated prodelta environment. These coarsen up into parallel laminated sandstones, in which the sands are interspersed with coffee grinds, which is the comminuted remnants of plant material that's spewing out from whatever vegetated landscapes the Prudo Bay rivers were feeding into. And then an example of another flooding surface overlain by a somewhat disrupted and wave laminated bay fill or prodelta shale. So we see these evidence of these sandstone units capped by these flooding surface forming local intra-reservoir seal pairs that were of great interest because a lot of these deltaic facies and overlying fluvial facies were filled with the oil and gas that was of economic interest. And finally, we start to see sharp-based erosional surfaces. So these represent the base of distributary channels with a nice mudstone rip-up lag and some small-scale pebbles showing up, overlying a cross-bedded to rippled farming upward unit of an underlying channel. So we start to see stacked channels cutting into each other and evidence of scours. We see nice evidence of dune-scale medium-grained cross-bedded sandstones. These make great reservoirs, finding upward into stacks of current-rippled, unidirectional current-ripple sandstones. And then there's another sharp contact with an oil-stained floor of a scour with some mud chip rip-ups representing multiple flood cycles as the floods in the rivers waxed and waned, leaving their record in the stratigraphy. As we start to climb up, we start to see the evidence of much coarser-grained fluvial units with getting into large pebbles and some small cobbles. And so we're starting to see evidence of pretty coarse-grained river deposits. Here's a nice example of conglomeratic fluvial deposits, moderate levels of sorting. The units are pretty coarse-grained. And you can see, based on the centimeter scale here, that we've got pebbles that are getting up to perhaps 3 centimeters in diameter. And of course, the size of the grains and the sorting is going to be important in trying to determine the shear stresses, the flow velocities, the size and scales of the rivers, their discharge. And ultimately, once we have a discharge, we can start worrying about the area that drained in order to feed Prudo Bay and the size and scale of the rivers. Here's an example of dune scale, cross-bedded sandy, pebbly fluvial sandstones, classic poorly sorted fluvial conglomerates, again, with the finding upward indicating waning flows in the bars and channels that built the rivers. We start to see mudstones interspersed with these fluvial deposits. They say beautiful evidence of mud cracks, pedogenic structures, and a red coloration, indicating that they were sort of moderately arid Paleosol environments. And this is an example of these red mudstones. You can see the vertical core behind with these mud cracks. And then on a photograph of the surface, you can see examples of variably oriented slicken sides, which are classically formed by these soil forming processes. So some of the big questions is, how do the sandstones correlate? How big were the channels that deposited the fluvial deposits in Prudo Bay and fed the deltas? How wide are the channel belts? How amalgamated are the channel belts? What's the connectivity? And are the rivers tributary, trunk, or distributary? We see a clear transition from gravel rivers to sand rivers. What controls that transition? And a question that I was not able to ask back in the 90s when I worked on this formation, I was able to think about it, but now 20 years later, I'm revisiting these sort of old rocks I worked on with a source to sink focus to see whether or not we can do an improved job of estimating the size and scale of the drainage basin. So this was the correlation that existed before before Bowtie and I got up to Alaska. And we weren't very happy with this correlation. It's what we call the pinch and swell engineering-driven correlation. So the gray represents the effect, the non-reservoir of the so-called havoc. Then the sort of salmon-colored was zone 1A, which was relatively low quality. Zone 1B was better, a little bit better quality, and zone 2A was the more gravelly fluvial stuff. And then the shale above it was called the Tango Shale. The unit below it was called the Romeo. And so our job was to look at all this oil and gas in this Romeo unit that had a lot more finer grained deltaic facies with some fluvial to figure out the organization. Now, what was interesting is that the BP engineers were requiring their geologists to pick these little thin shales. Some of them were 20 centimeters thick and correlate them as flat layers across the 25-kilometer long field. I said, sacre bleu. I've worked at Exxon on sequence stratigraphy. This is a delta. It should cliniform. For goodness sake, the shales can't be layer cake. So we went ahead and redid the correlations. This is the before, and this is the after picture. So you can see it's very different. What we said is, look, these aren't isolate sort of pinch and swell zones. There are dipping sandstones, and some of these cavic sandstones actually are connected up dip to oil-bearing sandstone. So it opens up for the potential for bypassed A in these distal cavic sandstones. They're in a separate lithostratigraphic unit, but are genetically directly linked up to the Ivishak sandstones. Also, you'll notice that in this view here, this big floodplain shale is just sort of included randomly in a flow unit, whereas we separate it out. And worse, these sandstones up here are interpreted to correlate. And we said, no, this sandstone is separated from that sandstone by a floodplain. So we had a completely different view of the connectivity. And so this is the big regional cross-section that Bowtie put together, putting together the work that we did together, which is the lower stuff, which is the deltaic. And then he ended up doing a correlations on a lot of the really amalgamated conglomeratic facies that constituted the middle and upper parts of the reservoir that by the time Bowtie got up there were largely filled with gas. So one of the things that we looked at is can we find evidence of single-story sharp-based finding upward channel fills to give us an idea of what the largest river deposits are in the field? And I've circled in green areas where we see pretty good evidence on the gamma logs and in the cores of sharp-based finding upward units that look like a single channel fill or a single channel story. That gives us information on the depth of the largest rivers And given the amount of well log information we have and the vast amounts of core, we felt that we could basically figure out what the largest river was that flowed over the floodplains that fed Prudo Bay Field. And so here's an example of some of the cores. And here I've shown the upward firing facies successions. The lower one in salmon probably represents 3 or 4 amalgamated stories. But in the Tango unit here, you can see these sharp-based single firing upward units with floodplain both above and below that indicates probably single story channel fills. To make a long story short, the maximum channel fills that we found were on the scale of about 40 feet. Yes, we worked in the US, or about 12 meters. Now, the maximum thickness of a channel story in an ancient system is probably represents a Talweg confluence scour. And so the actual mean bankfill depth is probably about half that. So the mean bankfill depth of the Prudo River is probably on the order of about 6 meters deep. So not a terribly big river, and certainly not a continental scale river. And here's just another example of a measured section showing the various interpreted bars and stories. A story would be a single channel fill consisting of a series of stacked bars. And you can use stuff like cross-set thickness and other observations to try to get at the flow depth responsible for depositing these channel stories. And again, the axis is in feet because that's the way the data are collected. And it looks like these channel stories, again, about 10, 20, 30, about 40, 50 feet thick. And we assume that would be maximal channel depth. So now we get in just some simple paleohydraulic estimations. And I'm not sure I've done this right. And if you have a better idea how to get at the, so what I want to know is, okay, so what was the shear stress? What was the slope? What was the velocity that moved the coarsest material, which is shown on the left, sorry. And so you can see from the scale here that the largest pebbles, they're about 2 centimeters in diameter. So this is a diagram from John Bridges' textbook from a short course that I took from him. He's got grain size on the bottom axis. He's got shear stress on the vertical axis. And so the assumption for this poorly sorted sediment is the largest pebbles are moving or rolling along as bed load. And the finest stuff is probably jumping up and falling back down as suspended load. And some of the finest sand that infiltrates the pebbles were probably in quasi-permanent suspension. So if we sort of pick the finer grain suspended load and the largest class that moving this bed load, we can get an estimate of the shear stress that was required to move these pebbles. And we get a shear stress something on the order of 12 to 20 pascals. Okay. Now from that, we can use the simple equations that relate shear stress to slope. So that's the rho GH, H is the depth, rho is the density, G is the gravitational constant. We're going to use 6 meters, which is the mean bankfill depth. We've got the shear stress from the shields from the diagram I just showed you, and we can solve that for slope. So the slope that we get is something on the scale of 2 to 3 times 10 to the minus 4. River slopes vary from about 10 to the minus 3 would be very steep, and 10 to the minus 5 would be, the Mississippi or the Euphrates River. So it looks like the Prudo Bay Field is sort of an intermediate slope river. Certainly not a flat river like the Mississippi, but not an alluvial fan or a fan delta, which is how it was interpreted sort of at field discovery. Now then we can just, simple tables, we've got the shear stress, and from that we can go in and we can calculate some critical velocities. So we've got a critical shear velocity of something on the scale of 12 to 14 centimeters per second to move those coarse grains. Then we can use something like the Shazy equation. The problem with that is it's for sandbed rivers, so we may be getting into a bit of trouble here, but it looks like the velocity was something on the scale of maybe 1.3 meters per second. Maybe it'd be a bit higher if we use a higher Shazy coefficient. Okay, now we've got an average velocity. We've got an idea of the bankfill depth. We don't really know what the width of the rivers are, but there's lots of cross plots that say given this depth, here's a possible width. So we're going to assume that a 6-meter river could be anything from 100 to 500 meters wide. That might be a little bit kind. And if we just plug that into a simple discharge equation, we get a water discharge on the scale of 500 to 2,600 cubic meters per second. And that's a pretty moderate scale river, not even close to something like the Mississippi. Okay, now, I'm not going to talk about all the errors in this. I've published a lot on the errors, and we can talk about that in question period. There are a wide variety of empirical power laws that relate either depth or discharge to its drainage area. And we have information on depth, and we have a guess at what the discharge is. To make a very long story short, depending on the estimates of these parameters, the power law B and the modifier A, we estimate that the drainage area required for the Prudo Bay Rivers might have been on the scale of 100,000 square kilometers. So now we've got an order of magnitude estimate on the size of the source area. Now, the good news is we have some ancillary information. So Miller at Stanford, I think, collected detrital zircon data from the Iveshak sandstone in outcrops. I would love to go back and do some DZ work on the cores. And she's shown the age here from 200 to 1,000 million years ago. Obviously, the rocks are Permo-Triassic, so you wouldn't expect any young zircons there. And she noticed that the detrital zircon pattern from the Saddle-Rochett Mountains, the Iveshak sandstones, were exactly the same as for the Sverdrup Basin. Okay, I'm not going to go into the details of detrital zircon analysis, but you've got the age of extracted zircons on the horizontal axis, and then the proportion of grains of a given bin of ages on the vertical axis. So there's the entire distribution on the left, and then she's just shown this window from 200 to a billion years on the right, which emphasizes the similarity. So once again, let's go back to the paleotectonic reconstructions. So here's the Arctic Alaska block in its position during the Permo-Triassic. And you notice that there's a variety of source descent systems that surrounded the Arctic Ocean. We've got the Trans-Laurentian River, we've got the Paleolina River, and then we've got the Sverdrup Basin, which is draining these highlands here, and then we've got the green dot, which is the Prudo Bay Field. So one of the questions is, was Prudo Bay fed by this Trans-Laurentian system, or was it fed by rivers associated with the Sverdrup Basin, so an intra-basinal river using the old Galloway terminology? So I went ahead and took Sue's examples of Paleo-Triassic rivers, and I just drew a little ellipse that represents 100,000 kilometers square drainage area. And it's pretty clear that it would be very difficult for Prudo Bay to be fed by the Trans-Laurentian rivers. And at any rate, the detrital zircon signature of the Trans-Laurentian rivers is completely different from the Prudo Bay rivers. So what was nice about this example is the detrital zircon data provided a nice test of my catchment area estimation that I estimated. So the Miller and et al. Work disallows a Trans-Laurentian origin. Now, Ash and Embry suggested that the sediments of the Sverdrup Basin may have been fed by this hypothetical crockerland. Again, I simply put my same drainage ellipse onto Ashton's diagram, and doesn't even look like Prudo Bay could be fed by crockerland. So it probably represents resedimented material deposited in the Sverdrup Basin. Okay. How am I doing for time, Paul? I have another bit of a story to tell.
Yeah, pretty good. Now it's on 9:40, so you're good.
Okay. So that was the basic story I wanted to tell you. Now, I've been in this game for quite a long time, so I thought I would just run through just a few examples of this is stuff that I've published, and just give you an idea of how we can continue to use this methodology of source to sink in the Cretaceous interior, if I may, and I'll run through this pretty quickly. So we'll try to make sure that we leave at least 10 minutes for questions. So during the Turonian, North America was split into a vast seaway, and there were a series of separate drainage source sink systems that fed into the western margin of that seaway. And I've been working on that for many decades now. And we've got these beautiful, extensive exposures. And one of the questions we had when I was at Atlantic Richfield Company is the Farron Delta a good analog for Prudo Bay? Now, it's a small source-to-sink system, and it got me thinking about, well, what's the size and scale of the rivers in these Cretaceous sandstones? And are they 6 meters like the Farron? Are they much bigger? Are they much smaller? The outcrops are fantastic. You can walk things out forever. And the great thing is, here's an example of our regional sequence stratigraphy. We've got incised valleys. We've got ideas of what the channel belts look like. And we see a beautiful transition from pro-delta muds into deltas and into coarse-grained fluvial systems. So the stratigraphy is similar to what we see in Prudo Bay, a delta to a pro-delta, all the way through to conglomeratic fluvial transition. Here's an example of an incised valley. So that tells us that we're in a trunk system. It's overlain by coal-bearing floodplain mudstones, and you can see the laterally dipping sandstones that represents a fluvial point bar contained within a floodplain that's contained within a much larger scour. And of course, that requires the large-scale scour to be the valley that contains the floodplain and the river. And the amazing thing about these outcrops is that you can see these hierarchies of fluvial scales. Here's an example of what the conglomeratic facies look like. And you see we've got centimeter scale pebbles, just like Prudo Bay. Here we see beautiful examples of what these channels look like. I love this picture of a preserved fossil tree trunk. And there's Young Lee standing next to a nice pinch out of a nice meandering stream. In the lower diagram, you can see beautiful lateral accretion sets of these single thread meandering rivers. Don't have a lot of braided rivers in the Farron. Of course, we actually like meandering rivers because you can get a better estimation of the width. And we use a method that was worked up by John Holbrook and his students, Juanis, that's the fulcrum analysis. So we work very hard in these outcrops to find these trunk streams in the incised valleys. And then we can do the same kind of analysis that I showed you from Prudo Bay, where we take the thickness of channel stories and depth of channel belts that we can see in the outcrops. We've got information on the grain size. And then we can even look at the elevation drop of the valley floor to get a direct estimate of the slope that the rivers ran across. In general, the Farron channels are about 4 to 5 meters mean bankful depth. Slopes are on the scale of 10 to the -4, very similar to the Prudo Bay Field. And drainage basins are estimated on the order of sort of maybe 50,000 kilometers, so maybe half of what we see in Prudo Bay. And the climate looks like it's ever wet. We can estimate velocity. In this case, we've got dune scale crossbedding. We know the depth of flows. We know the grain size. And so in this case, we simply used the Rubin diagram to estimate a probable range of velocities. So velocities range from something to 75 to 150 centimeters per second. We've got good evidence of the actual, we've got cross-section exposures that give us direct observation of the width of channels. We also have plan view exposures where we can see the width of the channels. And so we're pretty comfortable with our discharge estimates on the scale of about 400 to 2,000 cubic meters per second. There was a big question as to whether the Farron represented one river that avulsed, or whether the various deltas of the Farron represented several rivers feeding several separate deltas. Here's an example of the model. Is there one trunk stream that feeds a delta, like we see in the Po, or are there many drainages feeding the separate deltas? To resolve that, we went back to detrital zircons and collected a bunch of them out of the various valley fills. And interestingly, we found something we didn't expect. The Farron notum delta shows two rather different patterns. Okay, one pattern which shows an enrichment in younger zircons and a subduing of these older ones, and another that shows a pattern which has a very strong peak at around 1.7 billion years. And this is classic of rivers that are draining the Mongolian highlands, which is to the south of the Farron Delta complex, whereas this signature is more diagnostic of rivers eroding the severe thrust belt. We see that there are fundamental differences in the petrology. So the Mongolians show a greater enrichment in feldspar and less lithics, whereas the severe show a greater enrichment in lithic fragments. So we see fundamental difference in the provenance. When we went ahead and remapped the valley fills in the Farron, it's a compound valley fill formed over multiple cycles of sea level falls and drops. And we found that there were valleys that show this severe signature and valleys that show origin from rivers that were draining from the south. We have two completely separate drainage systems that are merging to build one big delta complex. That allows us to abandon the hypothesis of a single great river that was valsing and pushed us towards the idea that there were multiple rivers that were feeding a single delta complex. In the end, this is an example of well logs from the Farron. And we sort of said, well, how would you correlate these using the concept that there might be valley fills or they're all distributary channels? And here's an example of an outcrop-based correlation of the Farron. And you can see that it's far more complicated than what a petroleum geologist would do with subsurface data. I've been teaching sequence for many decades, and this is a data set that I give to students. And the question is, how would you do correlating this? So here's an example of correlation of the key surfaces. Here's an example of the facies filled in. Looks like a pretty good correlation. That student probably got an A for that. And then I thought, well, let me put together the varieties of correlations. These are all A quality students, and you can see that they're still very different. Some of them show amalgamated channel belts like an E, and some of them show a lot of Christmas trees with a lot more channels. And so, this is the dilemma for the subsurface petroleum geologist. How do things connect up? And to understand that, we need to understand the nature of the source to sink system. So here's an example of the map geology based on logging the outcrops on the left, and then an example of what you might do in the subsurface. And you can clearly see that we gain information by understanding the outcrop analogs. I'll sort of finally go back to what we correlated based on only subsurface data in Prudo Bay. The question is, are we over-correlating? Obviously, one of the ways you can test this is by looking at pressure and fluid flow data, and the question is, how do we do? Anyway, I'm at time, probably a bit over time. I think we probably still have a few minutes for questions. I'll stop sharing. We can pop the slides back if there's questions, and I will, in the time we have left, I'll see if there's any questions that anyone has. Looks like we're about.
Yeah, Jonah, the time is perfect. Thank you. This is a really amazing, fantastic talk. Thank you so much. Now we open the floor to the audience. If you have any questions, any comments, go ahead, unmute yourself and directly to talk to John. Michael, go ahead.
Yeah, so in Prudo Bay, you went and had the one drainage system at about 100,000, but could that also be a set of parallel rivers so that the drainage area might be several times larger?
Absolutely. Yeah, that's an interesting point. I think the way to test that, I think the easy way to test that would be to go ahead and start collecting DZs from across the field and see if there's any obvious indications. Having said that, you could have a large area that's got multiple rivers. Mm-hmm. I think the short answer is, in fact, I thought about this before I gave the talk today. Yeah, there absolutely could be. In fact, my paleographic reconstruction showed several rivers reaching the coast.
Right. Your first slide showed.
First slide, right. That. So indeed, each of those rivers could have a separate drainage system. Absolutely. And if there were several rivers, each of which was 6 meters deep, you could, depending on how many active rivers there were at the same time, like the Canterbury Plains in New Zealand was an area that we thought could be analogous to Prudo Bay. And then you could maybe up the drainage system you probably wouldn't change the length very much. You probably just simply add a bunch of circles, right? So
Right.
you could take my lips and put 5 or 6 of them, and then see, how much more area that would get you. It still wouldn't get you to a trans-Laurentian drainage because the DZ data disallow that, but it might mean you're accessing more of that Crockerland area. That's a great question. Yeah, one that would be interesting for us to test. Well, there's 5080 out there. Somebody else must have, and you can type a question if you feel more comfortable doing that.
Hi, Professor Janok. This is Srini from China University of Geoscience. Thanks for your excellent talk, and I am very interested in your sandstone correlation profiles. On your profile, I saw they're very thick amalgamated trunk channel deposits. When we saw the outcrop sections, we sometimes see the very, very thick trunk channel deposits. They can be like over 30 or 40 meters thick, but they are quite isolated in littoral. And sometimes it's wide spread and for a long distance. So from your opinion, what's the main control factor to control this, the littoral continuity of this trunk channel? Sometimes they are isolated and sometimes they are wide correlated for a long distance.
That's a great question. So the depth of an incision, let's say during a sea level fall, is going to be related to whether or not there are nick points exposed. A nick point is a line across which there is a change from a shallower to a steeper slope. Okay. Right. And the things that control nick points in the Cretaceous interior seaway are typically stranded shore face deposits. As a consequence, nick points in the Cretaceous seaway are seldom more than about 20, 30 meters deep. Okay. So valleys in the Cretaceous interior seaway are never more than about 20 or 30 meters deep, and there's a few exceptions. Now the width, and I actually ask students this question all the time, what controls the width of a valley is actually the duration of the fall or the uplift. So if sea level falls very rapidly and rises again, the river simply doesn't have much time to cut a wide valley, right?
Right.
So the shorter the period of fall, the depth will be the same, but the width will be much wider if the fall persists for a long time, because then the valley can start to cut. It's like the Colorado River is able to cut the Grand Canyon because it's been lifting up for millions of years, right? If the Colorado plateau lifted up and then dropped down in 100,000 years, the rivers would cut down, but it wouldn't have time to migrate and cut laterally. So the control on the width of valley systems is primarily a function of the duration of the time that the river has to cut a swath. So I'd say that, and time is the big factor there.
Well, yeah.
And also the consistency of the substrate. So, if it's a bedrock river, it takes a lot more work to cut laterally into bedrock. Although, in the case of the Colorado and the Grand Canyon, it still cut a 20-kilometer wide valley. What's interesting in the Farron, we actually call it a degradational landscape. It's actually too big to be a simple valley, and it's 40 kilometers wide, even though the valley is only about 20 meters deep, right? So it's a fairly shallow valley, but it's multi-story and it's extremely wide, and that implies that sea level was low for enough time for these rivers. And again, they're cutting into sediment, not bedrock, so it's not like they have a terribly difficult time eroding. But again, so that the short answer is, I think it's the duration of fall controls width, and the concept of nick points is what controls the depth of incision.
Okay, yeah. But shall we call the valley, or we just call inside the channel belts? Because this is different, because I see from the profile, the lower part are actually the deltic front deposits are embedded by sand and mud layers, and it's overlaid by the very thick trunk channel deposits. So shall we call it's valley or inside canyon or some inside valley, or just inside the channel, because we are still talking about the deposits on deltas. So I'm not sure how could we define the terminology of this.
Yeah, so I mean, I think maybe I'll share again, just help clarify that. You know, I did go through the story very quickly, so can everybody see that slide there?
Yeah.
So here, for example, you've got the incised valleys. Okay, they're incised valleys by definition because they represent an erosional scour that's much deeper, 20 meters, than the 5-meter rivers that cut them. They're associated with a shoreline, unit 7, that's degrading and eroding into the underlying units. So this is evidence of a sea level drop, right?
Yeah.
The valley basically gets shallower as it goes towards the coast, and eventually turns into a series of distributary channels that are these shallow channels here. And they're feeding these big deltas, and these are low stand deltas, right? So I glossed over the sequence stratigraphy, but the sequence stratigraphy allows us to define, you know, single story channels like down here that are feeding deltas versus multi-story channels that are sitting within incised valleys, right? So
Okay.
we can distinguish incised valleys, distributor channels, and trunk channels in the Ferrum because the stratigraphy is so well exposed. As Mike's question pointed out, it's actually a lot harder in the subsurface because all you have is a bunch of holes and some finding upward facing successions, right? You know,
Yeah.
and it's more challenging. I mean, you know, I'm an experienced stratigrapher, so I'm good at linking things up. So, you know, it would be a mistake to call all of this stratigraphy a delta. You know, every single one of these letters is one delta, right? And so unit 6 is a delta, unit 7 is a separate delta. And so unit 6 and 7 represent a low stand systems tract with several deltas that are associated with a prolonged sea level fall. The fall cut the valley and fed several deltas that ultimately, you know, the rivers in the channel degraded and then deposited delta that was shifted significantly seaward and eroded down into the stratigraphy, representing a basinward shift and downshift of facies, right? All of which satisfies the criteria of a sequence boundary as defined by Exxon many decades ago, right? So the stratigraphy documents that pretty well. Then up here, we have an incised valley. Unfortunately, that valley ends and there's no more Ferrum outcrops or subsurface, so we don't really know where the low stands are that upper fluvial unit fed. But we do see evidence for, again, multi-story incisions that are filled with river deposits in which the rivers are shallower than the incision that they fill, requiring that to be an incised valley by definition. And I'm not sure I would call it a canyon because that implies a much larger scale feature, but you know, a canyon is just a much larger incised valley. Does that help?
Yeah. I see. Thank you so much.
You're welcome.
Okay, any question?
One more question. When you were trying to estimate the bank full depth, you sort of said it's half the thickness of the single story. Is that based on it? You incised it and then it grows one more width to become super elevated? And
No, we've done quite a lot of work on this. Again, I had to gloss it over in the interest of time, but you know, we've done a lot of very detailed facies architecture work where we've got, you know, beautiful exposures of the channels. One of my graduate students, Muhammad Apuullah, presented a nice interpretation of confluent scours. I've had several papers on that, sort of attacking. I mean, Jim Best's a good colleague of mine, but they published a letter to Nature on confluent scours and said that they can be 5 times bankful, mean bankful depth, and that's true. But you know, we sort of really worked hard on how to identify a confluent scour. A confluent scour is filled with a very large outsized single bar foreset. And once that, so you know, these rivers come together, and there's 2 types of confluent scours. Tributary confluent scours, which is where several channels come together, and then confluent scours at the downstream end of a braid bar, right? So there's actually several scales of confluent scour. Tributary junctions are actually rare in the rock record and require several rivers coming together. Confluent scours at the downstream end of bars are routine. And so we've mostly documented the latter in our outcrops because we can see the scales of bars, right? You can also use, Leclerc and Bridge looked at scaling relationships of dunes. They point out that cross sets are typically 1/3 dune height. Dune height is typically whatever it is, 1/20th flow depth, or 6 times dune height can be flow depth. And so you can also use that as a separate test of flow depth. And in some cases, we've got you can actually see mud-filled channels that represent the abandoned channels. And that actually gives you, if you decompact the mud, a good estimate of the flow depth at the time of channel abandonment. So we use all these observations from the field to get at flow depths. The assumption is that the rock record is biased towards confluent scours and towage depths. And so therefore the mean depth would have to be, less than that. That makes sense. But I didn't have the time today to go through all the work we've done on facies architecture, but we've published a lot on that. So if you dig into my Google Scholar, you'll see the papers that we've done that really dig into the detailed facies architecture work to kind of decipher the paleohydraulic parameters of ancient rivers. It's not an intractable problem. It works better when you've got really good outcrops. And the reason why we work the Cretaceous interior seaway is because the outcrop quality allow us to get at these important parameters.
Right, but in Prudo Bay, you don't have the outcrop.
Exactly right. Right.
Hey, John, I appreciate very much your analysis and concluding about multiple river feeding one single large delta. And I have 2 questions. First one about the sea level role. So it is very clear based on the modern analog during the high stand, we could see multiple river, dump to that kind of the system.
Right.
But if you think about low stand, could be, all the multiple river merge, confuse into one single river dump to the one single delta.
Yes, exactly right. And, Mike Bloom's got a great diagram that illustrates greenhouse versus icehouse controls on exactly that. And there's 2 issues there. Well, obviously, there's a big slope control. So the lower the slope, given a given sea level change, the lower the slope, the larger the distance of sea level drop.
Yeah.
And the larger distance would promote convergence of separate drainages. The Cretaceous is a time, and this, again, we're publishing like fiends on this as well, as to what controls. We see unequivocal evidence of Milankovitch scale, high frequency sea level change in the Cretaceous all the way through. But it's pretty clear that the amplitude is far less than during icehouse times. Yeah. So, sea level drops are on the scale of a few tens of meters as opposed to 100 meters. So the Cretaceous would promote relatively small sea level drops that would inhibit the convergence of major drainages. And that's exactly what we see in the Farren. We never really see convergence of the drainages. And that's not what we were expecting. So, effectively, we've sort of proven the Mike Bloom model that high frequency, low amplitude sea level changes disallow convergence of drainages, which is why the mid-Cretaceous is a time of small drainages that never converge, right?
Yeah.
And the big drainages are during the Triassic to early Cretaceous, which is when the Manville rivers, which are continental scale rivers, building the tar sands. I've got talks on that, but I didn't have time to talk that today. And of course, the present day system, which is very much still an icehouse system, but it's also related to the tectonics as well. So you can't ignore the role of tectonics and gradients in controlling size and scales of rivers, right? So, part of the Cretaceous story is you had massive depression of the foreland, flooding of that because of excessively high sea levels. Yeah. And that basically broke North America into Laramidia in the west and Appalachia on the right, and with a bunch of small river systems, on those much smaller continents.
The second question, the reason I appreciate very much about that analysis because in the modern system, what we observed from the Yangtze, from Amazon, even the Po River you mentioned, Adriatic Sea in the Italy,
Yes.
there's always a small river from the peninsula discharge, contribute to that longshore dominate deltic loop. But
Right.
the challenge we are always facing is how, based on zircon that you mentioned, we can tell there are some different multiple sources, but how we quantitatively defined, how much from the main river, how much from the local small river, that's always a big challenge for us.
Yeah, I actually solved that problem. Unfortunately, never published it. We looked at
Maybe give another talk.
yeah. So I had a graduate student do a very nice project on the Brazos Delta, and the Brazos is very special because the Brazos River is man-made, and it was diverted in I forget the date. And when you take and there's Tim Della Pena has the cores that the John Anderson group took, and what's great is that the Brazos clays are all derived from erosion of evaporative highlands, so they're red clays, and they intermix with the Texas mud belt that comes from the Mississippi. And so you can literally look at the cores and use the GSA color chart, and you can quantify the ratio of Brazos directly derived muds versus the muds that come from the Mississippi aerially. And that's in a thesis done by my student, it's been so long ago, his name is on the tip of my tongue, Derek Rice, who went on to become a millionaire exploring for unconventional shales in the Pennsylvanian. So we did quantify that with that, but I thought long and hard about how we would quantify that in Cretaceous, where all the muds are gray, right? So is there a way to fingerprint the muds? We've done a little bit of work of extracting DZs from the sands with, most of the shales aren't shales, they're heterolithic. And if you do have very fine sands, you can get the zircons out. And we have looked at the Juan Lopez member, which is a fairly muddy unit. It's basically on a long strike shelf mud, be right up your alley, Paul. And that has 100% severe signature with not a sniff of zircons from the Mulligan Highlands, and it's basically fair and equivalent. So that's a mud belt that's completely derived from severe rivers that drain the severe, right? So, and moved it along shore, who knows how many hundreds of kilometers. So yeah, I work extensively on ancient shelf muds as well, and I've been grappling with the provenance of shelf muds, and it's a trickier problem. There's that amazing paper in the volume that JP Walsh edited. It's by the Chinese group, and they looked at mud clay compositions around the South China Sea and all the different clays from Taiwan and mainland China. And so there may be ways with detailed clay analysis to do the same thing in an ancient system, but it's tricky, right? And obviously in the Adriatic, you've got the Po, you've got smaller rivers, and that whole Adriatic mud belt has multiple sources, right? You can also do source to sink analysis to say, well, what are the volumes of suspended volume sediments associated with each river, and just do analysis of the size and scales of, and that's a classic sediment budget that, that's your expertise, but I think there's ways of attacking it. Yeah. And, fingerprinting is a key, right? There's some way you can fingerprint the clays or extract the DZs from it. There may be some luck there.
Okay, great. Let's see if maybe we have last question. If anybody have
a question, but a comment. So, you're talking about the number of channels in the Ganges-Brahmaputra right now. There's one main channel, the swatch of no ground. But if you look at seismics, it's clear that in the past, there were often 2 or 3 channels that were cutting through the shelf. It's not always just a single amalgamated channel. Yeah.
And that's a great point. You do your best in these ancient systems. You try to find the biggest channel. But Mike, you've asked me great. It makes me go back. Okay, so how many systems actually, even if we find a trunk channel, that doesn't mean that there's only one channel. That and clearly in the Farron, we've documented that there are at any given time 3 or 4 trunk channels feeding the delta, right?
Right.
Yeah, and so I need to go back and rethink the source to sink discharge estimates on that basis. And right away you've got a Magellan source area, you've got a severe source area, and they're active at the same time. So you got 50,000 square kilometers here, 50,000 square kilometers there. That's going to get you up to a much larger overall sediment in the downstream, but it does represent separate source of sink systems that are feeding into one sort of semi-localized area.
Okay,
Yeah.
that's great. So any other question, comments? If not, thank you, John. Again, this is a great talk, great discussion, and I think that's wonderful for this talk series. So this talk is also available on YouTube, and I think also there's also a copy in the Bilibili station. So take advantage, show it to your student. Okay,
All right.
great. John, thank
so
you
much for
again.
inviting me, and
Thank you.
thank you very much. Yeah.
Yeah, great talk.
Okay, bye-bye.
Bye.
See you later.